Let's create a DFA for this language W, where W contains neither the substrings AB nor BA. So looking at this here, we can kind of split this up into two subproblems, and then conceptually it's easier to understand the subproblems before tackling the whole thing. So we want to create a language where our string doesn't contain the substring AB, and then we can create a separate language where our string doesn't have the string BA. So starting with this first one where we don't have AB, what we can do is create our initial state here. We'll call this state 1. And then on transition A, we're going to go to a state, let's call this state 2. What this tells us is that we have one A exactly when we get to state 2. If we have an input string, let's do AAB. We feed in this string letter by letter. We cross off the first A, use that to follow the arrow, go to state 2. Now we're looking for AB. So to get AB, we need a B right after an A. So for that to occur, let's have a transition on B to another state, state 3. Now if we're at state 3, that means we've first had an A and then we've had a B, as indicated by the arrows here. So that's kind of the concept for this DFA, where finding if a string has AB or not. If we want this string to not have AB, then states 1 and 2 would be the accept states, because we want to accept any state where we don't have AB. Now it's going to be very similar for this BA state here, where W does not contain BA. It's the same thing, but the A and B are going to be flip-flopped essentially. So we have our initial state, and then we start with a B instead of starting with an A. We go to state 2, and then we go to state 3 with a transition on A. And then again, states 2 and state 1 are the accept states. And this works because we need to follow the arrows with the corresponding letter, and there's no way to get to state 3 without having a B and then an A. And then let's fill in the remaining transitions. So in a DFA, every state needs to have the entire alphabet coming out of it, meaning the alphabet here is A comma B. So we should have an A and a B arrow coming out of every state. So for this first one here, if we have a B, B is not really relevant here. We need to start with an A for AB to occur. So we can just loop on our own on a B if it's the first character. If we have B, A, B, it doesn't, like, it's gonna have the same exact outcome as if we fed an AAB. So we can just skip all the B's that come before an A, because that's when we need to start looking out for the B. All right. Now next state, state 2, we have a B coming out of it, but not an A. So on A, we can again just loop, because if we have a bunch of A's and then a B, that's, it's the same thing as just having AB. This string is still present here. So if we have an A, well, we can just keep looping. If these A's can go on forever and ever, then once we hit a B, then we know that we have the string AB. So we can just keep looping on A. And then once we get here to state 3, we know that everything has already been confirmed. We know that we have the string AB. So therefore, we can just loop on every character. So A comma B, because nothing will change the fact that we have the string AB from here on. Now we can do the exact same thing, but kind of inverse for the second DFA, the doesn't contain BA DFA. So we're going to loop on A here, because again, we're looking for a B first before we can see if, for BA to exist, there needs to be first a B. So A is not relevant until we get a B. And now we can loop on B, because the same concept as before, if we have an infinite number of B's and then an A, it still doesn't matter. We can just loop infinitely and we'll still have that substring BA. And then once we reach state 3, we already know that we have the substring in question, BA, so we can just loop on everything. Cool, so those are the underlying concepts. Now it's going to make it a lot easier to combine these into one. Now that we understand the underlying concepts, let's make the full DFA that encapsulates this whole language. So let's start as we always do with our initial state. We'll call this state 1. And essentially here, remember how we had those kind of two paths where we had, 3 states where we're going like this. Well, what we can do is we can have kind of, we can have kind of two paths. We check if we're on the AB route or if we're on the BA route. And we can do that by kind of splitting from the initial state. So on A, we can go one direction, and then on B, we can go another direction. So on A, what do we need now? Let's make states here. We obviously need some states to arrive on. So when we're on state 2, that means we have an A. So what are we looking for? We're looking for a B. Once that B occurs, we're going to transition to state 4 here. I'm doing state 4 because we already have state 3 down here. So once we have an A and then a B, state 4 is kind of like our dead zone. It means we have the string AB, therefore we can't accept. And now we can kind of do the same thing on the lower path, the B path. What do we need after a B? Well, we need an A to not accept. So on a transition A, let's go to state 5. And state 5 is going to kind of be our dead zone. But wait, this is kind of repetitive. Why can't A just point up here? It can do this. You can do either way. You can make it so that you go to this dead state here or you go to this dead state here. However, it's preferred that you simplify your DFA. So this means the exact same thing with just one less state. Computer science is a very optimization-heavy field, and we want to optimize wherever we can if it returns the same result. So essentially what we have here is a kind of a flow where we can, if we have an A, then a B, then we go to this dead state, or if we have a B, then an A, then we go to this dead state here, state 4. But we're missing some things. In every DFA, on every state, we need the entire language, the alphabet. The alphabet in question here is A, comma B. So looking at state 1, we have an A and a B arrow coming out of it, which is great. But if we look at state 2, we only have a B arrow coming out of it. So what we can do is we can put an A arrow somewhere, and that is going to make our diagram legitimate. So what happens if we have an A and then we have another A once we're at state 2? Well, it doesn't matter. So we're going to loop on ourselves. This is because if we have an input string, like I explained in when we were understanding the concepts, when we have an input string, it doesn't matter. We can keep looping on A if we have another A, because once we hit that B, it's the same result as if we have triple AB or just AB. Sorry for going over that again. I know I already explained it before, but it might be confusing if this is your first time doing DFAs and computer science. Anyways, so what are we doing on state 3? We notice that there's only an A arrow coming out of it. So what do? We can draw a B arrow to make our diagram legitimate. So we can again loop on B, because again, it doesn't matter if we have infinite many B's or just one B before the A, it'll still return BA. Now, what about state 4? We don't have any arrows coming out of state 4, so this is our dead state, as explained in the concepts before in the earlier part of this video. We can just loop on A, comma B, because once we're here, we know that we've already failed the criteria, so we can't accept. So nothing matters past that. Now, when we get to state 4, that means we failed the criteria. So any other state is an accept state. So state 1, state 2, and state 3 are all going to be accept states, because we only fail once we get to state 4. That's when we have an AB or a BA. But because this language dictates that neither the substrings have AB nor BA, that means that if we don't have them, we're good. So therefore, we're going to accept on every other state besides the state where we have AB or BA. So let's test with some input strings. So we can test with, let's test with this, AABA. Let's test with AAA. We'll test with BBB. And then we'll test with an empty string. I highly recommend that you test with more strings, obviously, but for the purpose of brevity in this video, I'm just going to test these 4 strings. So what we can do here is, let's do this first string, AAA BA. We can feed our string letter by letter, so A is going to go in. We're starting at state 1, so we follow this arrow up to state 2. That's where we are right now. Our next A, we're looping on ourselves. Next A, we're looping again. And then a B comes next, so we're going to state 4. And that's exactly when we have the substring AB, and that's exactly when our criteria fails. And then we have an A finally, so we just loop on ourselves and stay on state 4. And we do not accept, which is true, because the substring AB exists in this string. Now let's do AAA. So we're going to start with first A, we go from state 1 to state 2. Second A, we loop, and the third A, we loop again, and we accept. Now this is correct because we don't have the string AB, and we don't have the string BA in this string here, AAA. Now same thing kind of with this next string, triple B. What we're going to do is feed our first B in, so we're going from state 1 to state 3. Our next B, we loop on ourselves, and then our next B, we loop again. And this accepts, and that's true because we do not have the substring AB and we do not have the substring BA in this string here. Now what about the empty string? So when we have the empty string, essentially we're just going to be ending on state 1. We enter at state 1 and then we do nothing, and then the sequence ends, and we're accepting on that, which is true because we don't have the substring AB and we don't have the substring BA in this string here, which is technically nothing, but it still remains true. Okay, thank you. That's the DFA for this language. I hope everything made sense. Feel free to ask any questions in the comments below, and I hope this helped.